Let me share the screen first. Is it visible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we have the last class on 8th, I think, 8th December last week. So this week we have didn't have any class on weekdays. So therefore we have to arrange the class in Sunday. Now next class, or rather the fixed class, we'll have on every Tuesday, mostly from 11:30 a.m. And from the next class, what I will do, I will randomly ask few questions, and every day I will ask 10 of you, and that is kind of viva, an assessment, and I'll give you some marks on that. So every day I will ask 10 of you. So let's start the class. So we have discussed different important characteristics of bipolar junction transistor. Now we'll start with the switching behavior of bipolar junction transistor. Switching behavior of bipolar junction transistor. So we'll start with this. Now, so for switching, proper switching of any transistor, NPN transistor, so we need a circuit. So let me draw the circuit first, then I will discuss this. So this is the transistor under consideration, which needs some biasing. So this is the load resistance RL. This is the collector voltage VCC, and this is the transistor under consideration. Now this needs a circuit to drive. Just a minute. Let's draw this first. So this is the circuit which is required to drive the transistor in switch on condition. Okay, now how does it operate? So we need a pulse which has two level. Any pulse has two levels. One is the logical one, another is zero. One is high level, another is low level. So we need this pulse to drive the transistors. So how it will be on? Now the logic 1 or logic high, when this is logic high, then what are the states of the transistor? Let us see. So logic high means, what about this transistor 1? What about this transistor 2, transistor 3, and transistor 4? Let me ask, what about transistor 1? If this base of this transistor 1 is at logic high, anybody? Let me ask. Trina Vishwas?
On state.
Okay. Trina Vishwas, you just unmute. Roll number 101.
Yes, sir. Yes, sir.
So if we are at the logic high level at the base of transistor 1, so what about the states of transistor 1 and transistor 2? What about the states of transistor 1 and transistor 2? Can you answer this?
No, sir.
Okay, mute yourself. Arijit Pal,
Yes, sir.
can you answer this?
So I think on state.
Hmm? What about T1 and
Sir, I
T2?
think on state.
Which one? Both the T1 and T2?
No, T1, I think.
Hmm? T1.
T1, sir.
Now what about T2?
Yes.
TS means what?
To
Ujjwal Haldar,
Yes, sir.
বলতে পারবে?
স্যার T1 থেকে দুটোই অন স্টেট হবে।
Why? Explain.
স্যার যখন আমরা বেসে যখন একটা পালস দিচ্ছি,
হুম।
ওটা যখন
Pulse
পালস
দিইনি
দেওয়া
আমি।
হবে তখন এমিটার কালেক্টর অ্যাক্রস ওই
Pulse
প্লাস
দিইনি,
ভিএস
আমি হাই স্টেটের কথা বলছি শুধু।
হ্যালো
এস এমিটারে হাই ভোল্টেজ আছে, হাই লজিক হাই। Pulse মানে both high and low. I am not discussing the pulse. I am discussing only at the high state. When the base of T1 at high state. Did you get my question? I'm
Yes,
asking
sir.
when the base of T1 transistor at high state, what about the states of T1 and T2? You were saying both will be at on condition. Can you explain?
No.
Aditya Rai, Aditya Rai.
Am I audible? Hello,
Yes,
hello. Am I audible?
yes, you are audible.
The T1 will be on.
What about T2?
Sir, if T1 is on, then T2 will be off because both are NPN transistor.
T2 will be, I didn't get you.
Off.
T2 will off.
Sir, yes, off.
Why? Can you explain?
So because if T1 is on, then T2 will base of T2 will be connected to ground, that is low state, so T2 will be off.
Correct. So you are correct. So that means if T1 is on, what about this T2? Because when this path is open, that means the current can flow this, then this current will flow. So that means the collector emitter current will flow through this T1 transistor. That means collector emitter voltage is very small. So we can say that this point, this point is almost at ground potential or very low potential. Okay, so that is not sufficient to drive the T2 transistor. Okay, so that means the T2 transistor will be off in that state. What about T3? Again, T3 base is also connected with this. So that means T3 will be also off. What about the
Sir,
T4?
but T3 is PNP. Sir, T3 is
Okay,
PNP. Shouldn't it be on?
no, no, no. Though it is a PNP transistor, but it will be off
It
only
will be
because
okay,
the
sir.
base voltage is not sufficient to drive the T3 into on state. What about the T4?
Off. T4 should be off, sir.
T4 will be off. Why?
Sir, because it is connected to ground. Again, because there is no current flowing, so it should be connected to ground. So that's why base is grounded. So it should be off.
So T4 should be off. So that means this is all about the logic high condition. Now let us discuss the logic low condition. What about T1, T2, T3 and T4? Okay, so let me ask somebody else. Soham Chatterjee, Soham Chatterjee, can you answer this? Soham Chatterjee, so I think he is not there. Only his device is switched on. So I have to mark him. Next is DRI. DRI. DRI.
Sir, I don't know.
Are you regular in class?
Yes, sir. I was present in the last class.
No, no. I'm asking, are you regular in the class, not in the last class?
I just missed one class.
Okay. So you're not following the classes? You don't know that if the base emitter junction is not forward biased, what happens in case of any transistor?
Couldn't study properly this time.
Then you start from today itself. Okay, mute
Okay, sir.
yourself. Sandeep De,
Yes, sir.
feedback আসছে. Can you answer this?
T1 is off.
Okay, so T1 is off. It's very simple to answer this. What about T2? What about T2?
T2 is off.
Why?
Sir, T2 is off.
Why?
Actually, T1 is off.
Mhm.
Actually, sir. Actually, T1 is off. Then T2 is
What about T2?
T2 is on.
T2 is on. Why?
T2. Can't understand, sir.
Okay. You just see that whether the base have sufficient voltage to drive the base emitter junction on or not. As the T1 is off, that means this Vs will appear here, isn't it? And that Vs is sufficient to drive the base emitter
Yes.
junction into the on condition for T2. So that means T2 will be switched on. Okay. Now anybody want to say that what will be the condition for T3?
Off, off.
Why?
Base emitter reverse bias.
Hmm?
Base
Sir,
emitter
reverse
reverse
bias,
bias.
sir.
Which one?
Base emitter of T3.
Base emitter of T3. Because it's a
It's a PNP transistor.
so it's a PNP transistor. So that means as this junction is reverse biased, so it is in off condition. Okay, now what about the T4?
So T4 will be on.
No,
Why?
because it will have plus Vs at its base.
So that means this Vs, which Vs? The second Vs, isn't it?
Of T2, Vs of T2.
Okay, so Vs of T2 will appear here. So here you will get Vs. So that will be sufficient to drive the T4 into on condition. Okay, so that means what happened? I don't know what is happening. Okay, so this is in on condition. So this is how one pulse, and with this circuit, so driving circuit which is uh, given in this block is sufficient to drive a transistor, a power transistor to in on mode. Okay, now this is the simple circuit which we require to drive the power transistor into on mode. Now though the on switch on transient is not so simple and it has different phases. So let me draw this. Suppose the pulse or the current, suppose the current, the base current in the transistor T4 is like this with respect to time. So I'm just drawing the switch off transient here. So it will off in this instant, though it is off in this instant, but actual transistor current, so that means the collected current of the our transistor will change like this. So this is the off transient for power transistor. Okay. Now this time, the time when after the base current 0 also, it takes some time, okay, to reduce itself. That time is called the stage time. So this is called the stage time. And the rest of the time is called the off time, or rather as this is called the fall time, and this total time is called the off time. So we can write off time. Okay, now this T off determines the switching frequency of transistor, because I have already explained during the power diode discussion that how this on period, on time and off time decides the switching frequency of any device. So here also the T off, if the T off is very high, then we'll get switching frequency low. Okay, so generally for BJT, the switching frequency is generally low due to this off transition time. Okay, so how we can make this off time a little bit uh, less by using some external devices? So that I will discuss. So one of the way by which we can reduce the off time is by using negative base drive for BJT.
স্যার একবার এই স্টেজ টাইমটা কি বলবেন?
stage time is kind of storage time. Actually, here also between this base and emitter junction, there is a parasitic capacitance. So that is some storage storage charge problem is there, like the diode. In diode also you have seen that uh, in the off transient there is some storage phenomena, isn't it? So therefore there also it needs some time to recover fully. So here also between this actually that base emitter junction is kind of diode, okay, isn't it? So that means base emitter junction is a PN diode or NPN transistor. So there also you have a parasitic capacitance. Like let me show it here. Okay, so between this junction, basically this is your N, this is your P, and this is your N, isn't it? Now this between this P and you have a parasitic capacitance. Okay. This parasitic capacitance, what it does, it stores some charge. Okay. Now when the device tries to be switched off, then this parasitic capacitance takes some time to discharge itself. So that time is considered in this stage time. Is it okay? Now
Yes,
what?
sir. Okay, sir.
Okay. So negative base drive. How by using negative base drive we can reduce the uh, overall off time for a transistor. So that I will discuss. So I will draw a similar circuit as I have drawn above. So that means we have a T1 transistor. So this is your T1 transistor, and with this collector you have connected the T2 transistor, which is another NPN transistor. But with this one PNP transistor is connected, and that is the T3 transistor. Okay, my computer is getting hanged. So this is the T4 transistor, that means the power transistor which is under consideration. And here we have the VC and the load resistance RL. So this is the T4 and this is grounded. This emitter is also grounded, and here we have the pulse. Now here what we will apply, we'll apply some negative voltage around 5 volts suppose. Now how this negative bias in the 3 transistor, that's the PNP transistor, will help in reducing the negative bias. Sorry, using will be help reducing the off time for the T4 transistor. Do you have any answer for this? So that means when from the logic high, logic 0 to logic 1, that is logic low to logic high, then the T3 transistor will help. Can you explain this? So that means it is very clear that the parasitic capacitance which has been formed between this PN junction will be discharged in a more in a faster rate if we have a negative bias connected to T3. Okay. Is it clear?
No, sir.
Okay. Now just see that when we have switched on, so that means in which condition it will be switched on, in logic high or low, or T4 switched on. In which stage the T4 will be switched on?
Low.
So logic low level it will be switched on. And we are switching off means we are going from logic low to logic high, isn't it? So once this logic low to logic high, what will be the changes in this configuration? That means what about the T2? What about the T2? For this logic low level, what about the T2? T2 is on, isn't it? So T2 will be on
Yes.
to
Oh.
okay. So T2 will be on to off. On to off. Okay, so once the T2 is off, how the parasitic capacitance will discharge then? If T3 is also off, it is not possible. Okay, but if you can make T3 on, then the parasitic capacitance can be discharged, isn't it? Are you getting?
But sir, if T3 is on, then T4 will get off.
Which one?
T4 will be off then if T3 is on.
No, no, T3. I have actually my purpose is when I am switching off the T4 transistor,
Okay,
I am
okay.
going to on to off
Okay, okay.
state. So therefore, I am going from low
Okay.
level to logic high level. So this is the off
Yes.
transient, isn't it? So I want to switch off the T4 transistor. So therefore, I am
Okay.
going from, so this is the transient. I am from on state, from on to off I am going. Okay, now think about the T2 transistor. If the T2 transistor is off and T3 is also off, then this parasitic capacitance will not get any path to discharge itself. So therefore it takes more time, okay, to be getting discharged. So if we have the T3 transistor on, so then the parasitic capacitance will have some path to discharge itself, isn't it?
Yes, sir.
Now what is the path? to discharge, the path is this is the path through which the parasitic capacitor will discharge. You see, in the logic low to high, that means we are going to high state, isn't it? In high state, your T1 will be on. So that means this path will be through. So then the parasitic capacitor will discharge through this path. Is it clear? But if we don't have the negative bias, still the T3 will help to discharge the capacitance, but in a very lower rate. If we use the negative bias to T3 transistor, then the attraction force will be much higher, and the parasitic capacitance will discharge at a faster rate, and it will reduce the stage time or overall off time of the T4 transistor. By this, we can increase the switching frequency of our transistor. So this is one of the way. So this is called negative base drive. Is it clear?
Yes, sir. Yes.
Okay, so next we'll discuss one very important phenomena for our transistor, that is quasi-saturation. I've already mentioned this term, isn't it? Did I mention this term earlier?
Yes, sir. But you didn't
I didn't
elaborate
explain,
it.
correct. I didn't explain, but I mentioned this term. So first I will show that how that quasi-saturation, because it's very evident that the characteristics, we have three clear regions. One is called the cutoff, another is active, another is saturation. But quasi-saturation region is not very wide one. There is very small region in that characteristics. So how to maintain uh, the operating point near about the quasi-saturation region of the transistor characteristics? So for that, I will draw a circuit. So circuit is similar to that I have already drawn. So that means, so let me draw this part only, because other parts will be similar. So here we have so I'm not drawing this part. Okay, so this part will be similar. Here we have T2, here we have T3, etc., etc. And here is the base, and this is the transistor under consideration, that is the power transistor T4. And here we have the collector voltage VCC, and this is the load resistance RL or RC. Okay, now what we do, we connect a diode in this, between this collector and base. So this is the collector base, so this is the collector, the emitter, and this is the base. Okay, now you see when we are driving the transistor into switch on mode, then what about the biasing condition of two junctions? I think I've already drawn in the last class, isn't it? So if you can remember, you just tell me. So that means in active region is not yet fully switched on. That region is called the active region. And when the switch is fully switched on, and that region is called the saturation region. So active, if you have the notes, you can open it and you just tell me. Saturation, the collector, base, emitter, collector, base, emitter. You just tell me what is the polarity of B, E, and C in case of active region? What is the biasing states of two junctions?
B positive, E negative.
B positive, E negative.
And
Okay.
emitter
And for
yes.
this collector base junction, so that means this is forward bias. What about the
Active region
collector?
collector is positive.
Collector is
base
positive
reverse
and
bias.
base is negative.
So what is the biasing
Sir,
condition?
this collector is reverse biased. Reverse biased.
Reverse.
Bias. What about this saturation?
The base emitter same and collector base will be forward biased.
So that is the change. So that point, this already I discussed in the last class. Why I didn't discuss, but in active region, these two are one of the junction is forward, another junction is reverse biased. That I mentioned in the last class. Whatever. So let us assume these two things. Now, when we are in active region, that means what about the state of this diode? Because you see, here we have negative, here we have positive. So in active region, what about the state of this diode? In active region,
Reverse bias.
Reverse biased.
so the diode will be reverse biased. So that means no current can flow through this. So that means current will flow only through the base emitter junction. Okay, and if the base emitter current is getting increased, what about the state of the transistor T4? Transistor T4 will be in switching on state, isn't it? So once the T4 will try to enter into the saturation, or when T4 just entered into the saturation region, what will happen? Suddenly the polarity will be reversed, isn't it? Suddenly the polarity will be reversed. And what about the diode? What about the diode? When the T4 just entered into the saturation, the diode will be forward biased.
Forward
So
biased.
that means then this base current, which was flowing in when the diode was reverse biased in the active region, now this base current will be bypassed through this low resistance path. Okay, so it will be bypassed through this, isn't it? So therefore, the base current will not increase. Not only that, base current will try to reduce. So that means the transistor which has already been entered into the saturation region, now due to the reduction of base current, it will return back to the active region. When it will return back to the active region, again the polarity of this base collector will be reversed. Again the diode will be in the reverse bias condition. Again the base current of the T4 transistor will try to increase and it will be driven to the saturation condition. So this is how the state of the transistor T4 will be switched between the saturation and active region. Rather, it is better to say that the state of the T4 transistor will lie between the saturation and active region, which is called the quasi-saturation region. Is that clear?
So can you explain the current increase decrease phenomena once again?
Okay. So if the current is bypassed through this diode, then it has two paths basically. It has one path, so that is another PN junction BE, but this diode will offer less resistance compared to this BE. If that is the case, then more current will try to flow through this path, which path I have drawn, and less current through the base emitter of the transistor. So that means যে base emitter current আগে flow করছিল, so the base emitter current that is the IB current will reduce from its initial value. So the value when the transistor was in active region. Okay, বুঝতে পেরেছো? যে কারেন্টটা T4 ট্রানজিস্টরকে স্যাচুরেশনে ড্রাইভ করতে সাহায্য করেছিল, সেই কারেন্টটা রিডিউস করে যাবে যদি কারেন্টটা ডায়োড দিয়ে বাইপাস হয়ে যায়। And if we don't have the sufficient IB for T4 transistor, then the T4 transistor will not remain in the saturation region. It will return back to the active region. Is this point clear?
Yes, sir.
Okay, so now let me explain this point of this biasing. So you see, এই পয়েন্টটা যদি ক্লিয়ার থাকে তাহলে আমি একটু বলি যে এই যে তোমার পোলারিটির ব্যাপারটা কি হয়। Actually, the quasi saturation region, active region, all it has another perspective from device point of view. I am not going into that details because if I go into the device perspective, then it will take a longer time. Suppose, so this is the base current. We have the VCC, we have the resistance. We can write RC or RL, whatever. I don't know why my screen is getting hanged. So whatever. Can you see this circuit completely?
Yes, sir.
Okay. Now, this voltage, what is this voltage called?
Collector.
VCE, isn't it?
Yes.
Now current flow
Yes.
direction in this direction, this is the collector current direction, isn't it? It's the normal direction of current. So if we apply KVL in this loop, Then what will be the KVL? Can you tell me? The KVL, simple KVL.
Sir, VCC is
This is
equal to
equal to VC plus ICRL.
ICRL.
VC
VCE plus ICRL.
plus or minus?
Plus.
Plus, sir.
Plus.
Plus.
Okay. ICRC. Isn't it? Okay. Now what about this VCCE in terms of VBE and VCB? Bolo? Can we write this?
Yes, sir. Yes.
Okay. Now, if the current flows like this, and if the collector current is increased, what about this VCE? So let me write another form of this equation. It's RL, no? RL. So suppose if this current is increased, what about this VCC? Whether it will change VCC? That is a fixed voltage, isn't it?
Yes, sir.
Now what about this VCE? If this collector current is increased,
It will decrease.
Decrease it.
It
Reduced.
will decrease.
so it will
Re-
decrease, isn't it? Now if VC is decreased, what about this? Which will decrease? The VCB, because VB is fixed, determined by the base emitter biasing voltage. Okay, so that means in active region, when we are, just a minute, I don't know why it is not getting changed. Okay, so in active region, when we are providing more base current, which will increase the collector current. But this increase in collector current will result in less collector emitter voltage. That means less collector base voltage. So that means in active region, if this is the collector base voltage, VCB, so that will reduce. At some point it will be 0 and then it will be reversed. If the collector current is sufficient, then the VCB will be negative, and that is called the saturation region. Okay, so in that case, it will change its polarity to this. So that is called the saturation region. Is that clear? বুঝতে পেরেছো?
Yes, sir. Yes.
Okay. Now you have another device perspective. I'm just briefly telling you. If I have some time, how much time? Already it is 1 hour. Actually, if we draw the linear this thing, what are the different junctions or different substrate in this? This is n plus, isn't it? What about this? If this is your emitter and if this is your collector and if this is your base, what about this substrate?
P.
P.
What about the next? This drift
minus.
region n minus and this is n plus. Okay. So in active region, the excess carrier concentration or charge concentration is like this. Okay. So this is the charge concentration in the active region. Still, there is a space charge region here. Then what will happen if I go for this towards the saturation? What will happen? It will extend like this. It will extend like this. Okay, so when it will reach at this point, so this is called the saturation region. So when this curve will reach this point, this is called the quasi-saturation. This point is called the quasi-saturation region. These are the active region. And when it will like this is called the saturation. Saturation means we have a sufficient carrier density at this n minus n plus, that is the drift collector junction. We have sufficient concentration at that junction. That is called the saturation region. Okay. So this much we should say on this device perspective. Now the next point is safe operating area, that also I already mentioned but I didn't discuss. Safe operating area, SOA. Okay, so first I will draw, then I will explain it. Here you have the VCE. Basically, this safe operating area is given in any data sheets of any transistor. So therefore, we should know what is the safe operating area. Then we can safely operate our device. Just a minute. So we have 4 parts of the safe operating area. So let us name like this. So this is called the IC max, maximum collector current. Okay, now let us go one by one. So first line is AB. Okay, so first line is AB. which is called the peak collector current limit. So that means the current of the transistor should be kept below this limit. Otherwise, the device can be damaged. So that is the maximum value of the collector current beyond which it is critical to use the device. Okay, next line is called the BC, which is called the power limit. Okay, so that means here we have to see two things. That means the V less than VC max, because here we have two things. One is the VC and another is IC. That means the production of these two determines the power. But V at this point is basically below the VC max, because here you see this point is the VC max. Here your V is less than VC max and I is also less than IC max, but still you cannot uh, go beyond this point, because the power you have to consider here. So power should be below this. So that means if you have selected some voltage, suppose you have selected this voltage, okay, so that voltage is less than your VC max and the current also less than your IC max. So you are thinking that that is safe, but you have to calculate the power. How? By multiplying the voltage and current value at that point. And if it comes greater than the P max value, if it is greater than this P max value, then the device will burn. Okay, so that means you have to be uh, inside this safe operating area so that you can save your device. The next line is called the CD, second breakdown limit. Okay, so second breakdown is a phenomena. It is basically occurs in case of BJT only. So during the turn off, the operating point of BJT uh, must be located below this line. Otherwise, the device can be damaged. Okay, so obviously behind this phenomena there is some device perspective, but I am not going into that. But you have to select some point within this. Again, this value of voltage and current at this point, if we take the voltage and current, both the voltage and current will be less than the maximum values, but still the device can be damaged. But this phenomena generally occurs in case of transient, not in steady state. That means suppose you have selected this point. Suppose you have selected this point and your device is working properly. Okay, so then you are happy that your device is working properly. Now, when you will go for the switch off, then your device can be damaged. So that means this phenomena generally occurs during the transient, not in the steady state. Okay. So this is very clear. It's called the peak collector voltage limit. Okay, so this is basically the forward voltage blocking capability of the PN junction. So this peak voltage limit comes from the forward voltage blocking capability of any PN junction. So that determines this VCE max. So these are the 4 state lines which I have shown in SOA. So that means this area is basically your SOA, and whenever you will operate any transistor, you have to see the SOA from its data sheet. Accordingly, you have to select the operating point. So your operating point or the voltage and current at any condition, not in only steady state condition, in transient condition also, the voltage and current point should be within this SOA. Otherwise, there will be every possibility of getting the device damaged. That you should remember. Whenever you will go for selection of any device and you have selected your SOA, then you have to see its SOA from its data sheet, and you have to select your operating point accordingly. Is that clear? So this is all about this SOA. Do you have any question? Any question? Okay, so if you don't have any question,
This SOA graph is given in the data sheet.
yeah. Either the SOA graph will be given, or in form of points it will be given. Anyway, it will be given in the
Okay,
data
sir.
sheet. It should be given in the data sheet, especially in case of power transistor. Okay, because both this BC and CD is basically the power. It's coming from the power. The BC and CD line is coming from the power consideration. Okay, so one of the power is basically the steady state power, and this is a transient power, you can say. But AB and DC lines are the current limit and voltage limit. Is that clear? So therefore, when you will be
Yes.
you have selected your device, then you have to see properly the SOA of the device, and operating point should be selected accordingly, so that it is within the SOA. Clear? Then we'll be at the safer side. Okay, any other query? So next day I will start
Sir, in
the
BJT
device which is silicon control rectifier. হ্যাঁ বলো কিছু বলছিলে কিনা? কিছু বলছিলে?
Sir, in BJT, don't we have the reverse recovery phenomena?
Reverse?
Yes, sir. Sir, in BJT, don't we have the reverse recovery
No,
phenomena? Like there will not be any negative current even after turn off. Why don't we have such phenomena in BJT?
no. In this BJT we don't have the reverse recovery phenomenon. Okay, so there will be some reverse current. Okay, so there will be some reverse current and voltage as well, but তার চেয়েও যেটা ইম্পর্টেন্ট হচ্ছে তোমার টাইমটা। বুঝতে পেরেছো? অবশ্যই থাকবে কিছুটা। হুম, কিন্তু এখানে ডায়োডের মতো ওই রকম ক্যারেক্টারিস্টিক্সটা হবে না। You will have reverse current. So here also,
Okay,
because here also you have two junctions. Okay, তো এখানে রিভার্স রিকভারি হবে,
okay, sir.
কিন্তু রিভার্স রিকভারির জন্য ওখানে যে তোমার প্রোটেকশন গুলো লেগেছিল, তো এখানে প্রোটেকশন গুলো লাগবে না। যেন ওখানে আমার স্নাভাস সার্কিটটা লেগেছিল, উই ডোন্ট নিড এনি কাইন্ড অফ স্নাভাস সার্কিট।
Okay, sir.
Okay, anything else?
Yes, sir.
Okay, so if you don't have any other query, then what I will do, I will take the attendance. I think today you have renamed yourself properly, and I will note down the attendance. Just give me some time. So Ankit Jaiswal, roll number 2, roll number 6, 1002. You are lateral. Vikas Kumar Barnwal. Are you lateral candidate? I'm not getting. Okay, because Ankit also 1002.
Yes, sir. Vikas Kumar Barnwal is lateral.
So 0206, 03, Somnath Pal, 04 or
Yes, sir.
Okay, so I'm taking the attendance. 04 Arijit Pal, 06 Hasibur Rahman, 09 Amrita Dotto, 10 Deep 11 Saurabh Burman, 12 Sandeep De, 13 Trina Vishwas, 15 Ali Hamjan. I have 21015. One is Ali Hamjan, another is Ujjwal Haldar.
Sir, Ujjwal Haldar is lateral.
Ujjwal Haldar is lateral. Okay, thank you.
Sir, 1006. Okay, I am Kaushik Machi. I am the fresher, and that 1006. You told Hashimur Rahman he is lateral.
Okay. It's okay, no problem. Then I have roll number 17, 18, 20, 23, 23, then 26, 29, 30, 32, 40, 47, 49, roll number 49, then 53, then 53, 54, 59, 60, 64, 67, 69, 70, 70, 74, 78, lateral 10, lateral 10, lateral 3, lateral 6. Okay, lateral is all you have taken. Lateral 13, 14, 15 also have taken. And what is your roll number? Satyabroto Mondol.
34 0.
So you have to rename yourself
Hello.
properly. Okay. 34.
Yes, sir.
34. Thank you. So I have taken the attendance. So from the next class,
Sir, roll number 66.
eh? Roll number
Sir, roll number 66. 66.
66. ছিলে নাকি তুমি?
Yes, sir, I was there.
কিন্তু আমি তো নামে দেখতে পাচ্ছি না in order. After 64, then 67. 66, Anirudh Anand. Okay.
Sir,
So I
66.
have taken. Anyway,
Yes, sir.
Sir, roll number 29, sir.
29 reach him. Anyway,
Okay, sir.
as I told you that from the
Sir,
next class,
1004 sir lateral ওটা
1004 lateral. এমনি normal নেই তো না 1004? Okay.
হ্যাঁ স্যার অরিজিৎ পাল
Okay, ঠিক আছে.
ওকে
So as I told you, from the next class, we'll start kind of assessment, and that assessment is through the random oral question. I will ask you, and every day I will ask 10 of you, and the syllabus will be the latest one, that is the today's class. For the next class, the syllabus will be up to today's class. So I have taken, I think I have taken 5 classes for you. Started with general introduction to power electronics, then power diode, and today we have completed the power transistor. So these 3 small chapters we have covered. So on which I will ask a few questions. কেউ যদি absent থাকো, then I will give him 0. কেউ যদি থাকো অথচ ডিভাইসের সামনে না থাকো, then also I will give him 0. So remember this, and all this assessment I will add to the final assessment. So remember this. So I am stopping the class. I am stopping the session. I'm ending the session. So thank you very much.